All right, let's pick back up with some. This is Newton's law of universal gravitation. Okay. We've been using in physics one, you used F equals negative G little m big M over R squared. Okay. That's what we've been using, right? This is actually a vector, so this is kind of the part where there's some differences from physics one, right? The main thing is that, well, we want to have this negative right here is very important for us. This part right here, F is actually a vector, and what direction does it point? It points in the same direction as the unit vector for R. Okay, so R is R hat. Okay, sorry, it looks like an A, but it should be just the point up, not the little horizontal line there. Okay, um, and what this is telling me, right? This little r right here is the center to center distance. Okay. And this r hat right here is saying that it is the unit vector in direction of r. Okay. What it's saying, unit vector is a vector with length of 1, but it points in the same direction as r. If we multiply it by this, we can ultimately get the magnitude of the vector, right? Or we can turn it into a full length vector, right? Okay. And I just answered that right here. What is the meaning of r hat? R hat simply tells us that the for that the force points parallel to the r vector. Okay, and then the negative sign tells us that the force points opposite to the r vector, okay? Because it's attractive, okay? So r is from the center of one mass to the other, right? So for example, from the center of the larger mass here pointing to the smaller mass here, the center of the smaller mass there, and then you see that the force is getting pulled this way, so it's going opposite r because it's attractive, right? This planet is pulling the larger planet is pulling the smaller planet. And what you would also see is that this one, if we started r vector at little m and then drew it to big M, then this force would go that way. So, I mean, it's the same thing on both sides. It's just, I guess depending on whichever one you're trying to find the gravitational force for, right? To get this equation, this is to find the acceleration of gravity on a planet. All you got to do is take mg and set it equal to Newton's law of universal gravitation, g little m big M over r squared. And all you got to do is recognize that you can actually cancel out your little m's on both sides. And you've just got g equals g big M over r squared. That's how you can find the acceleration due to gravity on any planet. Okay. Big M is the mass creating G field, okay, or the grav field, okay. Big G is going to be our 6.67 times 10 to the negative 11, and the units for that are newtons times meters squared per kilogram squared, okay. That's our constant, our universal gravitational constant. And then R is the distance from M's center. Now, here's the thing, okay? For us being on the surface of Earth, we usually consider the distance. So, for example, right, if we wanted to find the gravitational field of Earth, we would need to know the mass of Earth, and then R would be our distance from the Earth's center. Well, we're basically exactly one radius away from Earth's center. So we can just use the radius of the Earth. It doesn't matter if you're on the ground. It doesn't matter if you're on the second floor of a building. It doesn't matter if you're on top of the the a skyscraper. It doesn't matter if you're in a plane. You are, you're close enough to the ground that where we can just consider it one radius. That's why, I think we did it with the gravitational potential energy earlier, that it was like a linear approximation or something, right? That's exactly the same case here. Like, you're close enough to the ground, so we might as well just consider it that. Okay. What I'm going to do here is I'm just going to write Newton's law, universal gravitation, all separated out, okay, over r squared, F equals g little m big M over r squared, F equals big G little m big M over r squared, F equals big G little m big M over r squared. I know this is like really, really fun, isn't it? Right? Okay, let me make sure you can tell my m's are capital here. F equals G little m big M over r squared. F equals big G little m big M over r squared. Okay, I got really sloppy there at the end, but that's okay. Okay, the force is going to be the same for both planets, right? Because that's Newton's third law. Okay. But if the mass, okay, so let's call x, let's make that little m, and let's make y big M, just for fun, okay? Okay, so if mass of x doubles, this becomes 2 times 2. Okay, and nothing else changes, so the force should also be times 2, okay? Okay, if the mass of y doubles, then this is times 2, and the force is still, again, times 2, okay? Really exhilarating, right? Nothing really too crazy. If mass x and y both double, well then little m is being multiplied by 2, big M is being multiplied by 2. 2 times 2 is 4. Okay. Oh, sorry, why did I write 2? It should be 4. Okay. The distance between is doubled. Now here's the thing that's important to consider. When I multiply this, okay, this is multiplied by 2, but it's also going to get squared with the exponent down here. Okay. So this is actually going to be a 4 on the denominator, which means that the force gets multiplied by 1/4. Okay. If the distance between is 1/3 as much, again, so I'm going to do times 1/3, and that also has to get affected by the exponent. So this is going to be 1 squared over 3 squared, which is 1 over 9. So you have a 9 in the denominator. This is going to get to be times 9. Okay, now here's the thing. If you haven't noticed already, this is very similar to electrostatics, right? Where you have the inverse square law happening here. If the radius becomes 1/3 of what it was, then the force increases by 9 times. That's inverse square law, right? And if both masses doubled and the distance between them is tripled, this is going to be times 2, and then the distance between is tripled, so this is times 3. That has to be multiplied by the exponent. So I end up getting 4 on the top and then 9 on the bottom. Okay. So then this is just going to be times 4/9. Okay. I can't really simplify that anymore, so I'm not even going to bother. Okay, and the last question here is talking about what would happen to Earth's gravity if Earth was twice the radius but had the same density. And I really don't like these problems because they're kind of tedious. They're kind of tedious to solve. But here's how I'm going to start. Okay, I have to start by addressing, let's see, twice the radius had the same density. Well, if it has twice the radius and the density is the same, then the volume had to have changed. So what I'm going to do is I'm going to use density equals, or sorry, if it has the same, the radius changes, then the volume changes, which means the mass has to change, right? So the density would need to be equal to mass over volume. Now, I don't know how much my volume is going to change by, so I need to actually do that first. Okay, 4/3 pi r cubed. Okay, well, r is going to be twice of what it was, but that has to be cubed. So 2 cubed gives me 8. Okay. So that means that in my density equation, my volume is 8 times what it normally is. If I want my density to stay the same, then I need my mass to be 8 times what it was as well. Okay? And then all I have to do is I'm trying to figure out what would happen to Earth's gravity. Okay, so that's asking me specifically about the G strength, okay? G field. So I'm going to do capital G, capital M over R squared, okay? Well, we already said that the mass of the Earth needs to change by 8 times, okay? And the radius of Earth is going to be changing by twice as much. Now, remember, that does have to be squared. So I get 8 here, and then this is going to end up being 1/4, okay? Okay. So I get 1/4 times 8 times G, okay? Well, 1/4 times 8 is just 2. So new G, or G new, is going to be equal to 2 what G originally was, okay? Okay. All right. That I think is the end of, yeah, that's the end of universal gravitation. Okay. All right. Have fun.